Professional mathematics really has one big trouble. It is actually boring as long as you don't know why you are actually supposed to be doing things in the way you are doing them. This is why it is of absolute importance that we teach children to find out themselves the that it is good to do things in the way in which mathematics does them. In that video, I will try to demonstrate a little bit that approach using the example of fractions. I will now explain fractions for everyone. It is quite a simple topic, but I learned that some people are experiencing real difficulties with it, and the actual explanation of that video is actually the Penrose's introduction to his book, where he's explaining math trying to not be Penrose. That's the explanation. That's the description that I would give that attempt. Right. Well, actually, he's explaining physics, trying to not be Penrose, but math explanations are integral there. So there you have it. Okay, let's continue with fractions. So today we have just a simple school topic, fractions. I'd like to demonstrate to you that fractions is really a topic that everyone can learn, and there's nothing special involved into it. You just have to be consequent. That's all it needs. Oh, we are having trouble there. Okay, well, let's do that. Okay, you know the common shape of a fraction from school. And I'm assuming that at least something you have seen at school, right? And it is usually written like that, right? A uh, that that horizontal line, and under that B. What does that actually mean? Well, first of all, when we are writing down something like that in mathematics, we should ask ourselves whether it actually makes any sense. The fraction makes sense when B is not equal to 0. And well, let's say that, of course, we could consider fractions of some funny type, so to speak, like 6 to 5 divided, I don't know, by pi. And don't be afraid if you do not quite understand or do not quite feel comfortable with that expression. It is anyway nothing of our concern for now. I'm just saying what we are not going to do. And we are not going to look at fractions like this. We're just going to look at fractions that are going to be like this. A is possibly something like, it could be 0. Special case, it could be 1, 2, and so on up to the number, I don't know what number, any number at all, and of course any number at all means we can go further as long as we like. And of course we also allow for negative fractions, so A could be also anything downwards in the other direction on the number line. So in the other direction, because we are going in that direction, when we are going in the negatives, right? We have 0 here, and we go like in a mirror image here, -1, here 1. So minus kind of indicates we go into the opposite direction to the usual direction from left to right. From left to right, we go with pluses. Pluses are usually omitted, right? And from right to left, we go with minuses, indicated like that. Okay, but if you are not familiar with these topics, you should be. For this video, it is then, well, you have to learn it somewhere else because, yeah, at least for now, I consider them rather too, I don't know, too uninvolved to teach them. Okay, well, fractions are actually of the same category, but at least, there is something to talk about. So go and learn that somewhere else, and later on when you understand how that works. Okay, so A can be all the positive numbers, positive counting numbers, all the, so to speak, negative counting numbers. Again, we could go to whatever, -1, I don't know how many zeros. Of course, I don't have to take those numbers to indicate that we are just going through all possible values. Okay, A could be that, B could be that, and here probably what remark should be made. It does not mean that A is kind of all of that at once, even though I write like A equal to ta ta ta. That's not what I mean. I mean that I am considering an object A divided by B, and that object could be all the different stuff that would arise from the different values of A and B. That is actually, well, how does it work? Well, I'm telling you, okay, I'm going to consider that object. And there are two ways to look at it. I could say, okay, I do not yet know, or I do not yet specify what A and B are going to be, but they are going to be some numbers where A is chosen as a number from that category, and B is chosen as a number from the same category, where I write it now. Oh, we could also actually take only positive B's, but let's just keep it general. 0 we exempt from that. 0 it cannot be. We said that it cannot be 0, so, and we go up same way, right? So there are two ways to look at it. One way is, well, A and B are some numbers with a certain value, so we think of them as numbers with a certain value, but I do not tell you what value they have, right? So it is some mathematical object where A has certain value, B has certain value, of course from the allowed values, but I do not tell you what those values actually are, right? So for your information, or from your point of view, they could be anything. You don't know, right? But they are certain definite values. Okay? Then I could tell you, okay, actually A is A equal to 3 and B is equal to 2. And then it turns out for you that that object, A, horizontal line B, was actually 3 horizontal line 2. And by the way, a short remark, horizontal line, we will discuss in a second what it is, but I'd like you to adapt a little bit that view that you are looking at a mathematical object and you don't need to immediately to know, you don't need to know what all the parts of the notation of that object mean, what all the constituents of that object mean. You can gradually discover what the respective constituents mean. Here we have three constituents. We have the upper number constituent, we have that horizontal line, and we have the constituent B. And always when you are saying something really, really crazy, again, you don't need to understand that, but just for the sake of I don't know what, well, let's say something like that. Then
even though you might not have a complete information of how to decipher it, you can nonetheless look at the particular constituents, and then due to the mathematical situation in which you encounter it, you could guess what another things have to be. Of course, at such elementary level, you are actually not doing that, but this is something to which it would be good to get used. Okay, so, and another thing, what I'd like to say, this tic-tac manner of teaching, and I'm starting one thought and I'm continuing with another thought. This is intentional. I wouldn't like you to learn mathematics from these lessons like you learn it at school or something like that. Instead, I would like you to go into the state of a mathematical thinking, even though it's such an elementary level. It is, well, I would like to go you into a pre-state of mathematical thinking. Let's call it like that. Okay, so another thing, well, we could view it as really an abstract object that just tells you, okay, those constituents are in that relationship. You don't know what that relationship means, not yet, or perhaps you know, but I'm just describing it like that, right? Perhaps you don't know. This is also no trouble. It is just a way of thinking. You don't know what this relationship is, but you know now these constituents, of which of two you know of their nature, they are in this relationship, these three constituents. And now this is supposed to be a mathematical object that could take one of those values but does not yet. That is, I do not just not tell you what the value is, but it does not yet take a value. The same with B. That is, when I do some operations with that object. And now be very careful. It is a very important aspect of mathematics. When I now would do some operations with that object in exactly that form, where both variables have not yet taken any values, then if I do such operations, that would be, in theory, valid for any numbers, for any allowed numbers that I could put into that. Then after plugging in definite numbers, so I would switch to the first consideration, my results of doing that stuff with the object would be valid for any choice of those numbers. So I can choose afterwards, not before I consider that and just say, well, it is two things of which I don't tell you the value, but instead after that, after I, for example, I could do that. If you don't understand it, no trouble. If I didn't even explain to you yet what the horizontal line is, and if you know that and just think of that in the way in which I'm trying to let you think about that, okay, I can do that, okay, because this is a number, a squared. This is namely a number that that I obtain in that I multiply a by a, right? And multiply a by a, no matter what of those numbers a might be, right? Theoretically, no matter what it is, I can multiply by it by itself, right? And then you could now switch to the safe perspective, like I don't know you what a is, but you could always, no matter what a would be here, you could multiply it by itself. Just imagine a is now 3, and you multiply it by 3. You could do that. Now I told you a is 5, and you could multiply a by 5. You can do that. A is 10, you can multiply a by 10. A is minus 3, you can multiply a by minus 3, which is multiply which is minus 3, multiply minus 3, and so on. And now, again, the second perspective where I do not tell you that a has some definite value, but instead I define for each of such multiplications this a squared as just whatever a you could take. Second perspective, whatever a you could take, but you do not take it, whatever a you could take, you could multiply it by itself, right? Okay, so, and I can then postulate that relationship. Again, if you don't understand how I come up with that, I do not yet, because you don't know. I have not explained to you what that notation in entirety actually means, right? But just you have to get used to it that you won't know it all time in advance. Okay, so if you do not understand that, that's okay, that's no problem. You just look at that and you see, okay, you see some stuff that you understand, you see some stuff that you don't understand, and you should get comfortable with it. Okay, so I could kind of calculate that, because the main idea is different. The main idea is I can calculate in that funny second way of perspective of looking at things. Okay, and that I do somehow. Before explaining what that line is, you don't know how, but somehow I can do that. Because here I have that object, which obviously is going to be a number, because, or at least you would first expect it to be a number because I'm squaring it. So I have to somehow be able to multiply it by itself, whatever it means. Because, well, you saw square there, you saw square there, and first you could suppose, okay, by analogy, okay, it should be multiplication of it by itself. So kind of would make sense. Perhaps you are wrong, but perhaps you are right. Okay, so, and you had some kind of transformation from here to here, and a transformation that gave you equal mathematical object. Okay, if that all has been confusing, this is no matter, it is meant to be. Okay, if you haven't understood many steps of those and so on, it was meant to be that, because I'd like you to get comfortable with the idea that you yourself have to find out which thinking steps are important and which thinking steps make sense in terms of in what way you should think about the thinking that has been applied. But of course, it will all be revealed now. And if you already knew that, just try to get into the perspectives of viewing things that way, in way of separating thoughts, in way of registering what is the important part within the thinking, and what the particular pieces of thinking are about and what they are not about, and so on. Okay, but now we will consider fraction properly. Now we just learned those two perspectives, and now I will just use them, maybe without emphasizing them explicitly. Maybe I will emphasize them explicitly nonetheless. We will see. I don't know yet. Okay. Moment. Now just a moment. I have to understand the way in which it works, because this is weird. Okay, let's say we do it like that. Okay. But I'd like to see all of them. Yes, exactly. Right. So, and now let's learn what a fraction actually is. Okay. We said what A and B are going to be. I won't repeat that. Okay. And then we just define that as another notation for dividing things, right? So A horizontal line and B under that, I define that, and this means I define that as something actually in the other direction. Moment. Just a moment. Huh? Okay, I didn't get that. Right. Right. So I have that new object, and that object, this is just the division, right? The division of number A by the number B. Okay. I just defined that new object, and it was new. You remember the two constituents we have discussed. But that constituent and how it interacts with another ones to give that actual object. Because if I only had A and B as constituents, then it would be just, well, A and B somehow taken together, somehow two numbers, right? But this actually makes out of those new object in that you add that third constituent that is meant to indicate a certain relationship between A and B, giving a new object, right? And that new object just turns out to be the result of the division of A by B. Right. And perhaps a few words on that. Of course, you know things like 6 divided by 2 is equal 3. If you don't know that, let's repeat why. Well, what does that mean? Well, if I divide something by something, then I look for the number which multiplied with the number by which I divide. Okay, so I'm looking for, let's not make an equation out of it. I wouldn't like to confuse you more. Okay, let's say exactly. I look for a number which multiplied by that number would give me that which I divide. I don't know how to explain it other than by means of an equation, actually. Okay, let's say number. This is number. And I told you that number, it's unknown number, so this is an unknown number multiplied by 2 is equal 6, and division of 6 by 2 just asks what is this number, and either you just use what you have memorized one time, or you even like think, well, okay, if I take that, so you kind of decide of how you come up with that. Okay, 2 of the1, 2 of the1, 2 of the1, so kind of should be 6, so you use your fingers, or I don't know. So but usually this is just intuitively you kind of memorize that, kind of understand that it is half that, half of that. Okay, so this is division. This is division when it is doable just completely, right? Then there are cases which you perhaps learned. There's another kind of division where we could do 3 remainder 1. What does that mean? Well, that means that we can do the division wholly for some part of the number in question, but there remains one little part which is not allowed to be divided anymore, so 7. And again, there you just use your intuition, and you're already having memorized certain properties of the numbers. You see that this is can be divided by 2, this cannot be divided by 2, so you have 3 remainder 1. But I wouldn't like to explain it now, because we are actually not interested in that, at least for now. We are just interested in the fractions, right? So this is one way to divide 7 by 2, but actually, and this is first, just accept it as a fact. By the way, an important thing, to learn to accept things as a fact, but only to find out why it actually makes sense to accept that thing as a fact. Just accepting a thing as a fact is a really, really bad practice. You should, in mathematics, you actually, in my opinion, should do it never ever. Okay. Well, Now accept it as a fact for a moment that there's some number that is exactly the result of that division. Okay, and I have not given you a simpler example for starters because I want you to learn to accept things as a fact, but to burn for knowing what that actually is, what is behind that fact. Okay, and we call that number. That is, this gives us a result. It gives us a number that is, by our consideration here, right? You have to think about it yourself, right? We said this asks for a number that multiplied by the number by which we divide, right? Number which multiplied by the number by which we divide 2 gives us that which we divide. So number multiplied by 2 equals 6. So by analogy, what we ask for here, and let's call it another kind of number, number tilde. So this is kind of one object, right? One notation. Okay. Here it was number. Here it is number question mark, question mark, question mark. Here it is number tilde. And now multiply by 2. That should be 7, right? Just by analogy, that just makes sense to think of that when you are thinking of that, right? Because it would be nice if it would have such similarity, what we are doing here to what we are doing here, right? And we claim that number does indeed exist. It makes sense to define it, right? And we just say for now, such a number exists. That is, there is a useful way to define it. If you don't understand what I mean by it, or what are the mental grounds on which it stands, no matter, you should just appreciate the idea that we could think perhaps we are wrong, perhaps we are right, perhaps there is no meaningful way to define that number, perhaps, but it could turn out that we can sensibly define that number, right? That would be nice, because then we could also divide something by that, divide something like that, and if we could get something sensible, then we could find such numbers which in turn multiplied by that actually give that, right? So, and well, now comes the classics. Okay, where could that be useful? Well, for example, we have, I mean, like, perhaps until now it was too abstract. So why would we even care, right? Why that object? Okay, mathematics, like find a number that multiplied by 2 gives 7. Why that? Let's imagine the situation. Now comes the classic, right? Let's imagine the situation. We have 7 pies, and you probably know what comes next. It is equal pies, but of course I'm not that great painter, so I'm not actually making them equal, but they are actually equal pies. And we have only 2 people, right? And each of them wants, in any case, to have equal number of pies. So of course we cannot divide in like that he gets 3 or he gets 4, he gets 5. No matter what we do, for another person there are either more pies to get than this person gets, or less pies to get, and they won't get comfortable with that. Impossible, right? And now if you think back to that problem, number multiplied by 2 is equal 7, then you could think, well, what would happen if we actually gave a portion, let's call it person 1. Person 1, let's call that person 2. And if we actually give a portion like that to that person, portion 1, and we call portion 1 P1 for shortness, and that is portion 2. If we give them some portions of these 7 pies,
right? So some numbers where 1 denotes 1 pi, right? Okay, so then they both insist on having equal portions, right? P1 is equal to P2, right? And then if we take those portions together, because we only distributed among them those 7 pi's, and remember, we just imagining that somehow we can create such a portion, both that makes both happy, and it means one gets exactly as much as the other, right? P1 equal P2, right? And P1 plus P2 should be 7, because when we take both portions together, then of course we get the original number which we actually distributed among them. Okay, but now P1 is equal P2, and of course it doesn't matter if I mean equal mathematical object. And remember, in mathematics it is always about meaning of the objects. The notation only conveys that meaning, right? It is always about the meaning of the object. I can just introduce new variable and not be confused by me introducing a new variable. I even call it alpha to confuse you more, or to make you more immune to confusion, right? I call that alpha just to not take either P1 or P2 to not make you confused. Oh, why do I take one and why do I ignore another? I could of course take either one to represent the other and only work with one, because this is same mathematical object. The meaning of equal is actually not just equal in sense of that thing is equal to that thing, but it is actually two things. No, the meaning of equal in mathematics is the same, but I rename them both for you to be comfortable. And of course, if I rename that object, since that is exactly the same mathematical object, this is one entity. I'm just having two different names for it and looking at that at one point of time and seeing that entity, and then I look at that entity at another point of time, but I see that same entity, and mathematics has no time. And this is just saying, it is not like you might encounter certain contexts in mathematics, time variables, but this is just a saying, a structure saying. You don't have to think about it a lot, just looking at that at different points of time. And I think, but I'm seeing same mathematical object. So it is really the same mathematical object in all times whenever I have that sign. And that just means I have two different ways to write that object, but the object is exactly same object the whole time. I'm just kind of I don't know, giving a different descriptions, but describe precisely that single object. So the keyword is single. So now I'm going to call it alpha. So the portion, the one person, which is the same portions of the other person, because we are only interested in numbers. Of course, it would be different portions of the pies. It would not be like the same portion, right, in the physical world, but we are interested in the number that signifies that portion. So how much they get, and they get equal alpha, right, equal to 7. But if I get alpha plus alpha, something like 3 plus 3, or 5 plus 5, then of course, just by definition, this is 2 multiplied by 5, right? The multiplication was defined exactly like that, at least multiplication by 2. I think this is not difficult, right? Multiplication by 2 was defined exactly like that, that we took some number, added it some certain number of times, and then called that number of times multiplication of the number that we added by that number. So n times, that would be just defined as n multiplied by 5. And again, n is a variable where you could just replace in your mind n by 3, or by 4, or by 5, or by whatever you like. Right, so this is actually 2 alpha equals 7. And now that situation we have already seen, haven't we? 2 multiplied by something gives you a 7. Number multiplied by 2 gives you a 7.
But I told you, in mathematics, names don't matter. So we could just suppose, perhaps same thing does it, right? And it would be actually natural to suppose that. But okay, perhaps you don't immediately see why. So we could just intuitively think, actually, it would make sense to suppose that this is the same thing. But it is same mathematical situation. Do you see that? When we look for a number which multiplied by 2 gives you 7, and we are only interested in the relationships between numbers. We are not interested in how they have a reason, right? This is the beauty of mathematics, that the way in which the objects have reason, the mathematical objects, it does not matter anymore. We get a pure mathematical relationship that is completely freed from all the constraints that would have been imposed on it by a particular situation. So we get number multiplied by 2 equals 7. And here we get 2 multiplied by number equals 7. Or of course, we can switch the order. Just think about it. If we have 5 plus 5 plus 5, of course, an example doesn't prove that, but it illustrates it. Okay, 3 times. And you could think, what would be 3 plus 3 plus 3 plus 3 plus 3 5 times? So you see, I'm interchanging the rows. Here it was 5, and it was taken 3 times, okay? And here it is 3, and it is taken 5 times. So the thing that comes with times jumps to the thing that comes that many times, and the thing that comes that many times jumps to the thing that was with times. And now you could think also of multiple other examples. Just make to yourself clear that that this 3 multiplied by 5, 5 multiplied by 3 makes sense, and that for any multiplication, this commutativity property, it is called commutativity, when we can interchange the order of multiplication, that it actually always makes sense. Just think about it. Okay, so 2 alpha equals 7 is actually mathematically exactly the same relationship as number tilde multiplied by 2 equals 7. And if you don't see the exact justification of why that is, it's no problem. But it is reasonable to kind of think in that way. Just think about it. What we are trying to describe it. Is it reasonable to think in that way, or is it not reasonable? And then we continue. Okay, so if you don't see exact justification, just think in way of, well, how would be the most reasonable way to think about it? Would it be most reasonable to think about it that this is completely different thing than that thing? Or would it be reasonable to think, oh, the relationship actually talks about those things that are exactly the same in that and in that, and the mathematical object involved are completely only about the relationships involved and about nothing else. Okay, so now the solution. Well, of course, visually you can see solution probably immediately. We can first, okay, but let's go slowly. We can first, from our 7 pi's, give one person 3 of them, okay, and we can give the other person 3 of them. So that we already did not, we first did nothing wrong, right? But 1 pi remains, and of course what we do is we divide it in half, and we don't think about specifics of reality, like pi might be, it might be difficult to divide pi exactly in half, especially when we consider atoms and things like that. But we don't think about that. We think of idealized objects, so the pi is exactly dividable in half, and so each gets a half and is happy. And if the persons live in the mathematical world, then they are actually absolutely happy, because this pi is ideal circle, even though I have not drawn it like that, right? This pi is ideal circle, and so they get just those abstract pies that are actually circle, and then we can really divide in half, or even better, we pie some numbers. So 1 is in correspondence to pi. I mean pi, not number pi, but pi like we pi it, right? But for mathematical persons, 1 could be pies, right? And so 7 is just same for them as 7 pies, right? But they are mathematical persons, and so it is actually 7 for them as food, 7, right? And we divide it in 3 plus 3 plus 1, and then, well, when we divide a pie into two halves, and now we come to that perhaps log-awaiting most simple example, we are going to divide 1 by 2. Again, why? Why is that exactly that operation? Simple. Because we are looking for a number, or for a number, just think of that piece, think of that piece, and if we suppose we have somehow created those pieces in the right way, right? If we have created those pieces in the right way, then multiplied by 2, the number that signifies those pieces should be 1. Again, 2 multiplied by number, let's call it number hat, should be 1. And we are looking exactly for a thing that does it. But what thing does it? Well, 2 taken some number of times is equal 1. This is analogy with multiplication, right? So 2 equal 2 taken some number head of times is equal 1. What does it mean? How do you take something a number of times and you get something smaller? Well, obviously, your number of times has to be itself smaller than 1. So your number of times has to be fractional. And this gives rise to the number 1/2. And 1/2, well, mathematically you might think, oh, what is this strange object? This strange object just, you could think of it, this is a number that multiplied by 2 gives you 1, okay? Another way to think about it, this is a relationship between any two quantities, where a 1 contains the other exactly 2 times. Why that? Well, let's see. When I get something like 2 multiplied by 4 multiplied by number, let's call it number index 4. This is equal to 4. Then I'm looking for, well, actually the other way around, of course. Yes, 4 multiplied by number index 4 is equal to, exactly. This is 4 multiplied by number index 4 is equal to, and number index 4 is just again a number that multiplied by 4 gives you 2, so it has no special meaning. I just ran out of options to write something proper above, right? That's why I do it like that. Okay, this is some kind of number which actually signifies that 4 taking that number of times gives me 2. What number of times again? Well, we could invert that, right? 2 given given the opposite of that number of times should give me 4. If you don't follow it completely logically, this is okay. We have not yet discussed the rigorous way to understand that, okay? But it is kind of, you could think of that by analogy. 2 multiplied by that number is equal to 1. Here 4 multiplied by that number is equal to 2. Right, so kind of if we think of that as something, right, something that multiplied by a number gives exactly its half, because 2 is the half of 4, because half of something is something that you take 2 times, okay, and you get the thing in question, and 2 you take 2 times, you get 4. So that number is again half. I have not yet called it half. I am doing that now. This number is actually half. And what have I told you? Well, no matter what we take, if we multiply by a number and actually get half of a number, but by what have we multiplied? What do you have to take from that number? You have to take the half of that number. And you see by these numerical examples, of course, you could just construct as many as you like, right? Okay, this is bad that I'm calling it the same, so I'm calling it 5. And you see, it doesn't have to do with numbers in question, it is just my enumeration. Okay, number 5, I'm calling number 6, that is equal to 8. And yeah, in any case, in any of such cases, the number that you would have to take would be the relationship between a half of a quantity and a half of a quantity and a quantity, a half of a quantity and a quantity. And you have to take that quantity a certain number of times in each of these things to get the half of that quantity. So what number of times do you take it? A half number of times, because taking that quantity one number of times gives you quantity itself, but you want the half of that quantity, so you get that number of times, exactly half number of times. And this is the factor that we look for. And of course you could construct infinitely many other examples, right? So, but this gives us an interesting kind of situation, right? We have discovered that, and now I'm just renaming those numbers that I had before. Convenience, I also do not remember all of those names. And we are only interested in mathematical relationships, so I'm not doing anything weird, right? I'm renaming them, but we are thinking of mathematical relationships, not of names. So you could just think here a blank, or you could think there something that fits here into such a relationship. What I call it is irrelevant completely. Except for you have to keep your notation somehow more or less tidy. Right. And we have that go to. And we have three equal 4. And we already said that all those would be satisfied by half. Right? And we could continue that indefinitely. 16, 16, 8, 32, 16, and so on. Right? Number 1. We already said that it is all a half. But we remember, now I'm reading that relationship into our direction. You'll see what relationship I mean in a minute. Right? We said all these numbers are actually half, which we denote like that, or we could also denote it like that. because this is actually result of that, right? And here the division is just written differently, right? It turns out that it is just very convenient to write in that way, and I will show you why. So you won't be left like thinking, why have we even introduced that? Why not stay by division? No, we will see that. But remember that 2 multiplied by number equal 1 was exactly number 1, number index 1 was the result of that. We had that somewhere. Yes, exactly. Number, no, not here. Where did we have it? I don't remember. Yes, 2 multiplied by number head was equal 1. And that was exactly the thing, that thing in that relationship corresponded to the to-find result in that relationship. So when we talk about 1 divided by 2, we talk about finding a number that multiplied by 2 gives 1, right? And of course, this is a symmetric relationship. That is, we can go another way when we talk about that. Then we talk about finding a result of that because this is symmetric, because we are just talking about how those mathematical concepts are connected in their nature. So there's nothing that would tell us, okay, you have to read it from here to here. You cannot go back. In that case, it is just the nature of those objects itself, and nothing here imposes directionality. If you don't understand why that is so, and I won't explain it any further mathematically, because here I want I want you to feel that mathematical nature. I don't want you to just see an equation and blindly juggle those variables around. I don't want you to do that. I want you to see that nature. Okay, so we can go back in the sense that that number was exactly the number that resulted from 1 divided by 2. Whatever it was going to be, we just supposed it will be there. And now we see it reasonably is there, and it is 1/2. But what is with those things? Huh? This is 1/2. Right, case clear. But this is 1/2 as well. But wait a minute, this is 1/2 because we have to take the half of that number. But wait a minute, it is not just 1/2 because this task was actually equivalent to 2 divided by 4. But wait a minute, that was actually 4 divided by 8. But wait, it is again half. So half is equal to 2 divided by 4 to 4 divided by 8? Eh? Yes. Take 1 pi, take 2 persons, and of course an example doesn't prove anything, but it just helps you to get comfortable, to see that it makes sense to define it like that, right? And then, what does each of them get? A half. Take 2 pi's. Take 2 persons, and each time, take 2 pi's, take 4 persons, and think what each one of them would get. And how do we actually do that division, properly? So how do we think about it? Okay, we could do it in that way. It is a very extractive way. First, we say, okay, everyone wants to get an equal share, so it certainly is not wrong to give a pi those 2 persons and a pi those 2 persons. Right? It is certainly not wrong. Okay? Because everyone wants to have equal shares, so we kind of would have to do that one way or another. If you don't see the exact justification, this is okay. Not in all places you have to. In some places you just have to trust your intuition, so to speak. Okay, and then 2 persons, 1 pi. Oh, we already know what that means. But what is that? 2 divided by 4. And we said what? Each 2 persons get 1 pi. What does that mean? Well, we divided those 2 pi's into the 2 pi's. And we kind of distributed them onto the persons, obtaining halves. But what is that? Well, and very important, brackets. Brackets just mean I mean that number that is in the relationship that I write here. If I want to have same relationship as I had here, exactly same relationship, then I have to think what constituents I had there, and the thing that I write after what should have, if I think about reforming the constituents, then I should formalize that this is the constituent, right? So this is the result of that application to which this relationship is applied. So that's why I put brackets here, okay? And here, 2, 2. So I kind of separated the persons in groups of 2, right? Plus means like standing close to each other, right? So this could be the meaning of plus, right? And here I separated the 2 pi's into 1, 1. And now I can separate, okay? 1 goes to that one. This is now not a mathematical application. This is just visual thinking. Okay, this goes to this one. Right. And now in the way of visual thinking, we would go as follows. The way of visual thinking, we would go as follows. Okay. Interesting. Mathematically, you cannot really reconcile that method. At least it seems to me like that. Wait a second, I have to think about it. Yeah, so these analogies have certain limitations. So these analogies help you to understand why mathematics actually work, but we could be limited to the concrete example. So the mathematical way would be actually different. The mathematical way would be like this. You take those 2 pi's, you have those 2 persons, just 4 persons, I mean. We are now dividing 2 by 4. And you have that pi, and you have those 2 persons. And now you consider those 4 persons as 1. Okay. And now you do the following. You first divide as 1, I mean, you now think of 4 persons. You first divide the first pi between the 2 groups. So instead of giving that pi to that group of 2 people, that pi to that group of 2 people, mathematics actually does something different. And you'll see in a second what I mean. It divides that pi into 2 halves and gives that half to that group. And of course, the result will be the same. Gives that half to that group, gives that half to that group. Okay, so, and you could, for example, say, well, now that gets 1 half, that gets 1 half, and there are something left, some things left, and some persons left who didn't get yet anything, right? And you get that pi, and you give the rest to those. And this is indeed mathematically viable because this corresponds to. Perhaps there is also the justification for that other method, but I don't see it without complication. So I don't see it in a way in which we would not create additional complications. That works. Anyway, again, I told you a wrong picture. What I meant, you take 1 pi. Yes, of course. Yes. It makes a lot of sense. You take 1 pi, you divide it into 4, and you take another pi, you divide it into 4, and then you divide the oh, if you divide 1 pi into 4, you can of course distribute it into 4 people. And then okay, so a mathematical way is very consequent. So it also makes a lot of sense. So a mathematician would not take a pi and give it to those two people, pi, and well, of course I'm talking abstractly, but kind of mathematics would not take that pi and give it to those two people, take a pi and give that to those two people, because it is not actually consequent, right? And this was a completely wrong picture, but now think of that situation like it would represent that situation, right? Uh, because that would not be consequent. Because if you take that pi, and gives those to people, and that pi is kind of left and not yet divided, and funny, right? But if you take that pi, so you work at each pi in its turn, and you separate it to 4 people. Okay, so in each step of a problem, you actually work consequently, right? That pi is completely distributed, and then you go on to another pi and distribute it among 4 people. All right. And of course, now everyone gets a half, just visually. Don't need to understand it yet mathematically. Right? And mathematically, that would be written 1 divided by 4, because I distributed that pi among 4 people. Right? And that would be 1 divided by 4, because 1 piece multiplied by 4 should give me a whole. Right? And that is, I took 1 out of here, and I took that 4 out of here, and actually I don't need that rewriting that I did, because actually mathematics would go consequently. It would take 1 pi divided among 4 people, would take another pi divided among 4 people, and here we have 2 things. I remember that was the task, 2 divided by 4, right? We have just rewritten that without actually changing its value, because 2 is same mathematical object as 1 plus 1. You remember, equality means same. Okay, and here we have 2 objects, right, that are same. So this is indeed 2, 4. And now, yeah, what I actually wanted to illustrate was, right. Okay, I kind of jumped in the thought, but this is usual. I mean, by all people who think parallelly of no, too fast in starting another thought without finishing the actual one, because it's just too clear, right? What I wanted to illustrate for you was that actually is logically same as 1 divided by 2. Why is that? Well, because that, exactly, that was my analogy with the 1 pi per 2 persons, and another pi of the 2 per 2 persons. Now we are arguing about that visually.
right? About that here, okay? And another pi per 2 persons. Right, and now you have to think of that in terms of the whole picture, and the whole picture tells you the following: we have two pies that we divided between two groups. And wait, how do I put that best? So so we are interested in the share of the pies that finally each person will get, right? Now we separated our task for division of the two pies among four into the two tasks of division of one pie between two persons into two identical tasks, right? But wherever we solve the original task of dividing two pies among four persons, and you can just visually see that everyone gets a half, or wherever we solve one of the equal tasks of a symmetric equal tasks into which we separated, I mean, if they are equal, they are symmetric, but yeah, this is just a visual perception. Um, or wherever we solve one of those tasks, the result of what the person get will be the same. And now you can think about that deeply, how it actually is exactly the same. Like exactly the same. The thing that you are doing in terms of relationships of objects is exactly the same whether you divide two pies among four persons or whether you divide one pie among two persons. And you can see visually that it works. Now you should wonder, well, okay, what is the useful, sensible way to formalize that? And indeed, the useful, sensible, mathematically consistent way is to do it like that. And usually, mathematical formalization for that is the following. You see, when you get 1 divided by 2, then you can multiply it by 1, right? And you take something, some number, no matter what number, you take it one time. So you get again that number that you took one time, right? So this is just intuition. So you take it one time, you get that number one time. Okay, but that one, oh, that one could be very different things. And now that one could itself be a relationship. I just claim it. That one is just a mathematical one. And we already said that it doesn't matter on what way we came to that one. It is just some kind of mathematical object. So it could represent many different things. Now we recall that thing again. Okay, let me think how to explain it properly. Uh, yes, okay, yes, okay. So now we have 1 pi per 2 persons.
Okay, so now we have those two separate situations that are actually equal. Okay, and now we think that we now now we'd like to have a representation for that one that makes sense to provide the bridge between that and that to show that it is actually exactly the same mathematical object. So that it makes sense to think of that as same mathematical object. Okay, so what would be that one? And this is not necessarily such a trivial question. It is not a mathematical, but rather a meta-mathematical question. What would be actually that one? And I'm not asking you to ask yourself that question, but I'm just pointing your attention to the point that it is not quite trivial. Right? What would be that one? I mean, not in terms of numbers, but what would be its nature? Uh, well, what do we have to formalize? Well, we have to formalize that the task of dividing 2 pies between 4 persons is same task as dividing 1 pie between 2 persons. And now we double. You see, if you want to get from those from that single task to that single task, and we kind of have to double both number of persons and number of pies. And why double? Well, they are symmetric, right? Situations are completely symmetric. And well, yeah, to get to the other situation, we have to double it. We have two completely symmetric situations, and we have kind of to put them together, which happens exactly in terms of doubling, exactly because those are respectively two equal objects. And now by objects I mean respectively 1 pi, 1 pi. So 1 pi, putting together is 2 multiplied by 1 pi. Or by pi again I mean a pi, so something that you eat. And here another object, a group of two persons. So same object 2 times. Again, we think of those just as numbers, remember. So even though those numbers now, this is persons, this is pies, but we are in mathematical world. In the mathematical world, persons or pies doesn't matter, right? The relationship that is within them is the relationship of numbers. Again, if you don't understand exactly what it means, does not matter, but you should kind of understand what it means, and you probably do, right? So our one is the multiplicator of non-changing situation. Basically, it is the it is the symbol for if we take such a situation and we take it 2 times, if we take 2 times exactly same situation of dividing our pie, then of course we could just take any of those particular situations and divide in that situation and just do the same in the other situation, and the mathematical action or the thinking action or the action that actually happened in the world would not give any new information if we take that situation multiple times. So, and this is what this one is. This is the index of unchanging of the information about mathematical relationships, whether we take that situation one time or multiple times. One time taking that situation would correspond to 1. To 1 meaning 1 taken as 1 with no further representations that would represent taking that situation, right? Because 1 is divided among 2. Right? 1 divided among 2. Okay. But now that one, it is mathematically same situation of division, no new information about mathematical relationships is given. What I mean by that, this is a very crucial moment. No new information is given, and this is complicated, but you have to understand that no new information is given means that carrying out that task is already completely carrying out that task of dividing 2 pies among 4 people is already completely covered. The process is completely covered, the relationships are covered, everything is covered as soon as we know how to divide 1 pie among 2 people. Okay, think about it, let it sink. If we know that, we already completely know that, so absolutely no mathematical information is involved. The situation is asymmetric, and doing that kind of is already encoded in just one thing taken like that. Okay, but if we take that situation 2 times, then we have to think, oh, what is actually involved in here? What actors are involved in here? Right? And those on one layer, this is one layer. Here we just get to multiply those 2 actors, that one actor by 2 because it's completely symmetric, right? Completely equal. So we have to multiply that actor by 2. So that actor has to be multiplied by 2. 1 multiplied by 2. Okay, this is what is happening here. When we get to the situation 2 pies divided by 4 people. And here we have to take those 2 people and we have to take those 2 people. But what we said, it is actually not changing mathematical relationship at all. So it is not giving any new information, not changing the relationship. So actually, this is what our 1 does. And this one, for that case, for that row, is represented as 2 divided by 2, where this 2 divided by 2, of course, per se, this is clear, 2 pies, 2 persons, everyone gets 1, right? So it is 1, but in that, the relationship that it represents, when we'd like to see that one in that analogy, is much more complicated. That one kind of means the unchanging nature of taking and doing that 2 times instead of doing it 1 time. And those 2 and 2 means how that unchanging nature would be encoded, what would be happening intrinsically in the system that we are actually considering. And you might think it is too complicated explanations. Why do I make it that difficult? Well, it's exactly the opposite, because you don't have to remember those explanations in all entirety, but you have once heard them, and whenever you have one aspect of fractions that is kind of funny, you can think of these explanations partially. You don't need to understand them, or you don't need to recall them. You have to be able to come up with them, or with similar explanations, or with explanations that suit you. You have to be able to come up with them because you experience that will at first to come up with the answers to the why. Why does it make sense? How does it make sense? And this is just one of the infinite analogies that could be given to properly explain that. Okay, that multiplication by 1 is same as that. And this you already know from school as shortening the fraction. If we have common factor in the numerator and in the denominator, you can put it away, and actually you could think of it as showing that the relationship that is encoded by that situation is same as the relationship is encoded by that situation. And of course, now you should think of all possible fractions. Do just some examples, whatever you like draw people, draw those pies, and come to terms with that this really makes sense. It is not like it is there set in stone somehow, and that it is I don't know, that it has to be completely clear to the utmost, to the deepest ground. No, you just have to see that this is the thing that makes most sense if you think of those things. And of course, you might think in the beginning, for example, oh, I came up with that. That is actually also makes sense. Perhaps this is true. Perhaps this is true in mathematics, and perhaps this is true, but perhaps not, because you only learn to really make mistakes really seldom in what makes sense when you get sufficient experience. So you might think, well, okay, it perfectly makes sense to me, but perhaps you have just not seen the whole picture into which it should be put, because that really takes experience, and that takes kind of some development of things that are based on other things that your thinking gets into the mode where you see what makes sense and what doesn't make sense. And even professionals do mistakes when they suppose that something makes sense, and that it turns out that it actually does not necessarily make sense in the way they thought, right? So this is normal, and you have to explore in that way, and you have to have your ideas, like what makes sense, what doesn't make sense, and at the same time you have to compare it with the traditional teaching, with what all people talk, with what all people tell you about those objects, how it would make sense, whether your idea is right or wrong, in that you compare it to what other people actually, to how other people actually treat the corresponding objects in math, and so on. Right. So do it for 3, 7, and 3, 5, and I don't know, whatever you like. Right. This is the idea of shortening the fraction, or of eliminating the common factor in the fraction. This is what it is actually about. And now, important thing, you saw we discussed quite some things. A lot of it, or most of it, was actually all around and about. It was not the actual topic, right? And mathematically, we have really not done much in the exact mathematical way of doing things with symbols and so on, right? And the thing which I'd like to emphasize now, we have not formulated some rules of calculation or something like that. Not yet. We will do that, but we have not done it yet. We have just discussed more like what fractions are about. And here it is important that you don't take things from it that weren't actually in it. Of course, you can suppose, oh, that actually would make sense. Of course, I would encourage that, right? That you have your own ideas. But don't take things like you think, oh, he actually explained that very solidly, that this rule is like that. No, I did not yet. Do not interpret into that some solid rules whilst I have not yet given them. First, I give you just some idea of how to think about things, of how to think more in the way, not in the way of explicit pictures, but in the way of how. Right. So, what is the way of the way to think about mathematics? About to think at least about these objects. Mind you, the way of the way is not the same thing as the way. So the way that I gave you was pretty arbitrary. Makes sense, yes, but there could be infinite more ways to make sense of things. But the way that I gave you, that really matters. All right. Okay. So what we wanted to see, well, that one half actually has those multiple representations. Right? And you can again do it with fractions, what, however you like, and really try to write it down, to appreciate that it exactly works that way, that this one represents that similarity of situations doing the same, having no information. Just think. However, it actually does not make sense to define things exactly like that way. People did not do that because it has to be like that, but simply because it makes sense. And make sense means here something very abstract. It could mean make sense for applications. It could mean make sense for picturing the relationships in the best way accessible to the humankind. It could mean just make sense based on the relationships between objects. It kind of feels right. It could mean lots of different ways. You have to in the best case to find him all eventually. Okay, so now, now, of course, in the same way, you could now discuss that you divide 1 among 2, you divide 2 among 4, you divide, I don't know, 8 among 16, and so on. For now, actually, what we learned is to appreciate the meaning of equality between 1/2 to 4th, 8 16th, and well, the actual rules and so on, which of course we will motivate in the same ways of the proper thinking, which I hope is fun for you. We will discuss it next time because wow, it became already a lot. I have not expected that to make it really appreciable, that you have to think that you could think in that way, that the way in which people think about these things and the way in which people deal with these things actually makes perfect sense from everywhere around, no matter how you look at it, no matter from what corner you look at it. And usually, I have to add something. Usually, when you think something doesn't make sense, how people do something in maths, if it is actually established math, usually, sorry, that means you are wrong. In the like, I don't know. I think I never managed to break maths, even though I thought a lot of times that I managed to do that. So it's usually you who are wrong, right? Okay. So, that is that. Okay. So, was quite a lot of stuff, even though we have just discussed the nature of 1/2. And remember, equality, again, one last time probably for that session, equality is same mathematical object. And here it expresses a relationship, or at least it is a way to think about it. Because there is a rigorous mathematical way, but we are now more interested in the intuitive properties that it should be done like it is done, right? Or that it could be done rather like it is done. And then to shoot, there is not a long way from that, but better it could be done. Better. Even always keep in mind that arbitrarity. Perhaps we could have defined things completely differently. Perhaps aliens have completely different mass. There are hints that point towards some things just being completely having same shape in any way, no matter what maths it is, no matter what abstract maths we could think of, but it is never certain. Okay, so that equality means it is same mathematical object, and we could think of it as just expressing exactly same relationship. Okay, so and this is also same, and this is what 16 82, 52, 64, 64, 128. You get the idea, I think. Okay. And of course, you are welcome to like play with that. 4, 4, 4, 8. So So if you carefully consider that and draw the spies and those persons, I don't know what is your favorite, like I don't know, bricks and whatever, bricks and I don't know, containers for bricks or whatever, like, right? Play with it around really, and try to make it interesting for you. So try to do it really in an exciting way where you ask yourself, oh, how does that work? Why does it work like that? If you are troubling with, if you have trouble with anything of that I explained, or if you have trouble with equalities that I have not explained, try to find out why it makes sense to suppose those equalities, or perhaps even to try to derive why it should be like that, at least in the frame of the explanations I gave. So that those explanations already gives that, at least if you accept those explanations that probably make sense, then things should look what I claimed them to look like. All right. I think that's it for today. Thank you very much for your attention, and I hope you enjoyed that introduction to thinking about fractions. Let's call it like that. Okay, let's, yeah, till next time.